All right, let's talk about naming ions as well as naming ionic compounds. But first, we need to kind of refresh ourselves on what charges particular atoms tend to take. The following are all preferred charges within ionic compounds of these elements. All alkali metals, that's sodium, lithium, potassium, rubidium, cesium, and francium, all take a +1 charge. Alkaline earth metals, the second group on the periodic table, takes a +2 charge, so beryllium, magnesium, calcium, etc. And then aluminum, zinc, cadmium, and silver all have fixed preferred charges as well. We do not normally see other charges for those elements. For on the other side, on the non-metal side, we'll see that group 15 typically takes -3 charge. Group 16 usually is -2, and you can see the examples. And then group 17 usually takes a -1 charge. And as you can imagine, an ionic compound is held together because of positive and negative electrostatic interactions. And so we see that coming together. However, we should name these ions first. We'll see that for cations, we will look at the following. This is a sodium atom, Na. Sodium with a plus on it is called a sodium ion. With this, we don't need to worry about noting that it's +1 because sodium will always be +1. There is no exception to this rule. Sodium is always +1, and so we will just call it a sodium ion. It's understood that it will be +1. This, for example, is a calcium ion. Calcium is in group 2. Group 2 always takes a +2 charge. And silver, is one of those 4 that we listed at the bottom. This is a silver ion. Every other metal, though, can form a variety of different ion charges. For example, titanium can come in 2 common charges. There are others. It could be titanium 3+ as well. There aren't fixed rules for these. And since there aren't, we have to indicate so in the name. So for this one, we would say it's a titanium 2 ion, and this one would be a titanium 4 ion. So we indicate the charge of the ion in Roman numerals. For example, this one, if you look on the periodic table, find W, it's tungsten. And this is a 6+ ion, so we'll indicate that with a 6 in parentheses. So if your cation is one of these, alkali metals, alkaline earth metals, or one of these 4 elements, you don't need to put the charge in parentheses because it's understood. And in fact, it's wrong if you do. So we don't ever write aluminum 3 ion because aluminum is always +3. And chemists are always about brevity. So if we can be lazy and not write something, we will not. All right. With the negative ones, thankfully, there are no exceptions. We don't have any weird variable charges here. And so, for anions, we just have one convention, sorry. We will take the name of the elements, for example, oxygen, and the ion oxygen prefers to form. This is an oxygen atom. No charge. This is an oxide ion. We're going to see that we'll take the name of the element. We're going to generally remove its last syllable and put that "ide" ending on, followed by the word ion. For example, Cl- is chlorine, is the element. When it becomes minus, we're going to change that last ending. Instead of chlorine, we're going to get rid of the kind of last syllable here, and we're going to write "ide" instead. So this is a chloride ion. This is Hydrogen is a non-metal kind of. Well, hydrogen's a very strange atom, but we'll see that later. This is hydrogen, right? The name. We are going to end up crossing off that last syllable here. We call this a hydride ion. And then we have, oh, I don't put that on our list, right? H minus is the only one that's can be negative. So don't forget that one. Nitrogen. This is a nitride ion. And then finally, we have polyatomic ions. They already have names. We don't need to name them. This is carbonate. And that's it. They already have their names. So that's why we have that big old chart that you're going to want to learn the names of all of these. Because as we'll see, with naming ionic compounds, we simply put the names together. And we have to charge balance the compound as well. So, for example, if we were to say we're going to make an ionic compound between sodium ions and carbonate ions, we'll see that when we need to do this, compounds must always be neutral. That's one thing we need to put here. So let me put this in. Let's put it in light blue because it's super important. Compounds must always be neutral. So if we're making a compound out of ions, we need to make sure that the charges cancel out. So if we want an ionic compound between sodium and carbonate, we need to make sure that we have enough positives to cancel out all the negatives, and vice versa. So one way I like to do this is what's called the crisscross method. We're going to need, for this, since carbonate is a 2 minus charge, sodium is a 1 plus charge, we need 2 sodiums to cancel out the carbonate. And so that 2 minus of the carbonate becomes the subscript for sodium. So we are going to write Na2, which indicates we have 2 sodium ions, and we only need 1 carbonate, so we're going to just leave that alone, because sodium had the +1 charge. So if we move that 1 down to become a subscript, we don't write 1s in chemistry typically, so we don't need to worry about it. And the name for this is we just take the names of the ions and get rid of the words ion. So for example, sodium ion, carbonate ion, get rid of those together, and we just call this sodium carbonate. If we were to put those 2 ions together, we just get rid of the ion as part of their name, and the name of the compound, therefore, is sodium carbonate. So just the same things as the ion names without the word ion. If we have, for example, titanium 4 plus and N3 minus, we can do our crisscross. So this 3 becomes the subscript for titanium, and the subscript for nitrogen becomes 4. This is titanium 4 ion, and the nitride ion, and so we will indicate titanium 4 nitride. One thing to note, if we have something like this, when we put them together, we technically get the following, Ti2O4. Because of the way ionic compounds are structured, as we will see in chapter 12 at the very end of the semester, it doesn't make sense for us to have multiples if we can cancel things out. And so we always want to reduce to what's called the empirical formula. Empirical means it's got the lowest number that we can have. For example, we know if titanium is 4 plus, oxide is 2 minus, we just need 2 oxides to balance out the titanium. So it doesn't make sense for us to write Ti2O4 when TiO2 works just fine. And both of this indicates titanium 4 nitride. All right, so useful thing there. All right, if we have multiple of a polyatomic ion, though, for example, if we have, say we have titanium and peroxide, let's not use titanium anymore, let's use, how about chromium 6? Why not? If we put those together, if we have multiple of a polyatomic ion, we need to put parentheses. Otherwise, we're going to have O26, which is not true. That's too many oxygens. For multiple polyatomic ions, use parentheses to enclose your polyatomic ion. It should be noted that when we're reducing this to get rid of extra numbers, never change your polyatomic ions. So never change polyatomic ion subscripts. So that's the ones within it. So O2 2 minus must always have that 2 at the bottom. We can reduce the 6 outside. That would work. So we get CrO2 3. And this would be chromium 6, which is the name of chromium 6, the ion, peroxide. Because peroxide is O2 2 minus, that's a polyatomic ion. Remember that we just need to remove the word ions from this. So we can't ever change the number within a polyatomic ion. So sulfate must always be SO4. That 4 can never change, in naming at least. So that's the last thing. However, if we want to find out the charge of something, say we have if we want to find out the name for given a formula, we need to figure out what ions are part of this. So if we're trying to do that, if we are given the formula and you want to find the name, you want to figure out what charges are at play. And so, generally speaking, our nonmetals are always fixed charges, right? So, sulfur is always -2. We have 2 sulfurs. We can figure out what manganese is, right? Manganese plus 2 sulfurs must be 0. That's what charge balancing is all about. We have to make sure that our positive and negative cancel out. We know sulfur prefers a 2 minus charge, so we can plug that in. So manganese -4 equals 0, so manganese must be +4. And so that means the ions here are Mn4 plus. Sulfur, of course, must always be the -2. So we would call this compound manganese 4, because that's the name of that ion, sulfide. And that's how we would do it. So, simple algebra here, nothing too crazy. Practice, practice, practice. You'll have hundreds of problems in lab to go over on this, so we'll work through it. All right, in our next video, we'll talk about some more naming of covalent compounds and acids.